A new quantum RF system could outperform antennas in jammed environments. Instead of relying on a traditional metal antenna to capture a signal, the system uses lasers to monitor how incoming radio waves disturb the atoms. While most people associate quantum technology with futuristic computers, the Colorado-based company Inflection is betting that the first major quantum breakthrough to reach the real world could instead happen in radio frequency, RF, sensing, the technology behind GPS, radar, wireless communication, aircraft navigation, and military surveillance. The company recently unveiled a new atom-based approach to detecting radio signals that could eventually replace parts of conventional antenna systems. They named this approach quantum spectrum. Interestingly, this new approach arrives at a time when the global radio environment is becoming increasingly chaotic. Every government depends on radio frequency signals to navigate, communicate, detect threats, move goods, manage airspace, and operate critical infrastructure. Those signals are now easier to jam, spoof, hide, and overwhelm, the Inflection team notes. Traditional RF systems rely on antennas and electronic hardware that are often optimized for limited frequency ranges, forcing engineers to build separate systems for different bands. This creates size, power, and reliability challenges, especially in contested environments. Inflection claims its new approach could bypass many of those limitations by using atoms themselves as sensors, turning excited atoms into radio detectors. At the heart of the system are Rydberg atoms, atoms whose electrons have been pushed into extremely excited states using lasers. In these states, the atoms become extraordinarily sensitive to electromagnetic fields, including radio waves. Instead of relying on a traditional metal antenna to capture a signal, the system uses lasers to monitor how incoming radio waves disturb the atoms. Those disturbances can then be translated into information about the signal's frequency, direction, and strength. The idea is not entirely new. Physicists have spent years studying atom-based RF sensing in laboratories because Rydberg atoms can naturally interact with a very wide range of frequencies. However, turning this quantum phenomenon into rugged hardware usable outside controlled lab conditions has proven difficult. Quantum systems are highly sensitive to heat, noise, and environmental interference. Building a portable receiver that can survive real-world deployment, especially in military environments, has remained a major engineering challenge. According to the researchers at Inflection, its quantum spectrum platform replaces conventional RF front-end hardware with a three-step quantum sensing process. First, lasers excite atoms into Rydberg states. Then, incoming radio waves interact directly with those atoms. Finally, optical systems read out tiny atomic changes and convert them into usable RF information. As the atoms themselves act as the sensing medium, the same receiver can theoretically operate across an enormous frequency range, from hertz to terahertz, without needing multiple antenna systems. This wideband capability is one of the most important claims because conventional receivers often struggle when trying to monitor many parts of the spectrum simultaneously. Atom-based systems, in principle, could detect signals across vast frequency ranges using a single aperture. Where antennas fail, atoms do not, the researchers added. The Inflection team argues that this could allow earlier detection of threats, better performance in jammed environments, and improved identification of hidden or spoof signals. In the US, the researchers are working with the Army Research Laboratory under a project called Robust, Integrated Quantum Electromagnetic Receiver, RICA. The goal is to build a transportable quantum RF system that soldiers could potentially use in environments where GPS signals are unavailable or under attack. In the UK, the company is leading the Quantum Direction Finding, QDIFI, project to identify the exact direction from which radio signals originate. That could improve long-range navigation and signal tracking, especially at low frequencies where traditional antennas become too large. Meanwhile, in Australia, Inflection is developing its quantum-optimized broadband Rydberg atom, COBRA, receiver, which combines quantum sensing with AI algorithms that automatically tune the system for better sensitivity and bandwidth.